Good morning. So today we are doing half of the XCM content. So the XCM content is 7 modules. I'm going to go through quite a bit of material. How many of you already have done a bit of XCM? I know at least one person here has. Any? No? Okay. Just the one. 2, 3. Okay. Fine. Well, let's start. Okay. XCM is a language um, that we created um, largely to enable parachains to talk to each other. So for this first bit of discussing XCM, I'm going to try and get you familiar with the concepts that we use, some of the syntax, some of the notation. There's some resources that you might want to look at and kind of understand where it fits in the stack. Okay, so Polkadot, rewinding back to Polkadot 1 rather than what I was core jam stuff that I was talking about yesterday. Polkadot is about sort of allowing a platform where security can be shared between many different blockchains, right? Now with core jam, we're sort of altering this so that security can be shared with sort of essentially arbitrary code execution. But for Polkadot 1, we're talking about like these very synchronous, linear state transition systems, blockchains. Now, it's all very well sharing security and saying, well, you know, we've got like just a single sort of token base, and staking this token base, being a validator means that you are securing not just one chain, the relay chain, but 50, 100 chains, all doing their own thing. But one of the very important advantages, it doesn't, I mean, it's great, it's very good, but one of the very important advantages is that if they're all sharing the same security, that they can all interact with each other. Yeah, that the state of one can directly impact the state of another. Because if it can't, then although it's good, you can still sort of share. You can have a single. Let's just say it's cheaper to do security. It's not like it's categorically not as good because these will become isolated systems. So XCM is part of the solution for allowing these different chains, different parachains to interact. Concretely, well, yeah, blockchains, cryptocurrency assets, NFTs, allowing them to interoperate on for these kinds of things is one very particular use case that people find as important. Polkadot, quite governance heavy, and one of the ways that you know XCM can be used is through allowing things like voting and enactment of votes via that might happen on one chain to have actions on another chain. And for that, you need some sort of way of communicating between the chains. And actually, quite importantly, if you've got sort of relatively like causally entangled systems, like for example, you've got you know a bunch of collectives in governance and they want to hold assets. You're stuck with either putting them in the same system so that they can, the collectives can command the assets, or you need some way of communicating, of like interoperating for them to do it across different chains. Now, of course, we don't really want to have to put everything that might be causally entangled on the same chain. That would defeat the point of scaling, right? So we're back to this thing of, right, well, if they're not all going to go on the same chain, then we need some way of allowing the different chains to interact and to do so in a relatively rich fashion, right? We're not talking about, an atomic swap, which was one of the, like, just sort of saying, I've got an asset here on this chain, an asset here on this chain, and I want to do in a single action an ownership swap of those assets. This is one kind of cross-chain interaction, but it's a very, very basic one. And you'll find in other ecosystems, they do have these very basic, very specific, very niche cross-chain interaction patterns, largely because they don't have shared security. So they have to sort of fall back on very particular little mechanisms that work in a very specific use case, but they're not very general. They're not general at all. Okay, good. So Polkadot's really sort of pushing this single use case chain with its there's an RFC, I forget which one it is, maybe 34 or something. But it's basically saying rather than have the relay chain host all of this system level functionality, we should actually have several different parachains that host this functionality, and the relay chain should just do its job. Now, this will become particularly the case with CoreJam, but even with Polkadot as it stands, this is the path that we're sort of moving down as we offload application level functionality from the relay chain, stick them onto what we call system parachains. One of them is the collectives chain. This is like a largely governance focused chain. Another one would be the asset hub, which you're probably familiar with. There's another one, the bridge hub, which you might have heard of, and there's another one, the identity hub chain. All right. So XCM specifically is a language, right? It defines a language. It doesn't define a data pathway. It's a language for communicating one's intent in a fairly abstract way. It's not a particularly sort of concrete thing. The different chains implement and support the XCM language in different ways. Yeah, they don't all support all of XCM. They couldn't really support all of XCM because it's like a sort of, it's not Turing complete, but it's a bit like a scripting language. It has all sorts of possibilities that you can do, as you will come to see. There are a large infinite number of XCM programs that don't mean anything, or that couldn't possibly be executed. Yeah, so it's not like there is just a handful of things that you can say. You can really do a lot with XCM, particularly with the abstraction mechanism known as locations, which we'll coming on to soon. So it's for communicating intentions between consensus systems, right? Between systems of which, but essentially global singletons, right? These kind of, that's what I kind of mean by a consensus system. It's like there's one of them, but they're not localized anywhere. It's not like there is a server and someone might push the off button. Yeah, there is only one Polkadot, but there's no off button to push. Yeah? So it's a singleton, but it's global, universal, ubiquitous. Another way of putting it. Yeah, so I'm not going to labor this point too much, but the idea is that it's not. We don't want to limit ourselves specifically to a blockchain communication system. It could, for example, work reasonably well with a smart contract system that is not necessarily at least a whole blockchain. It might be a portion of a blockchain or something. So we talk about consensus systems rather than specifically blockchains. As I said, XCM is a language or a format So there are utterances one can write in XCM. Those utterances have meaning. XCM tells you what those utterances mean. So it's a sort of syntax, but it's also semantics. Yeah, a language. It's not how you get it from A to B. That's a different thing. That's XCMP. Now, apologies for the rather confusing naming. Just adding a letter on the end makes it a different class of thing. It's a bit of a silly name. We have been looking for other names, to be honest, but nothing has really rung right in my ear. So we're sort of still at XCM and XCMP. But for what it's worth, XCMP, and that's not the only protocol. We have UMP, DMP, bridge protocols, right? There are many ways of getting an XCM from A to B. And then the naming is also, I think we're going to come to this later, so I'm going to delay that point. So yeah, it's versioned. XCM, when you write a message using XCM, you and send it, there's like a kind of container that it goes in, and it tells you what the version of the XCM is. They're not yet. If you're familiar with version systems, you'll probably have seen maybe some systems that also support not just versions but extensions to those versions. So you can kind of pick and choose sort of bits of a provision, bits that might make it into a new version. OpenGL was the first time I saw this. So in OpenGL, there are different versions of OpenGL, but before a particular feature might go into OpenGL, you'll see a bunch of names that says what extensions are supported, and you can kind of like check to see if an extension is supported, and if it is, then you can kind of use it in your OpenGL utterances. CPUs do something a bit similar as well. XCM doesn't support this, but it is sort of being mooted. It's come up a few times in the development, and I think it is probably something that's going to come in eventually, but it needs to be done the right way. At the moment, there's an RFC process for like suggesting alterations to the XCM language spec or whatever, that is just in its infancy. Okay, yeah, naming. You can say XCM message if you want, I don't really care, but XCM stands for cross-consensus messaging. Cross-consensus message format, XCM format, cross-consensus message format. An XCM system, a cross-consensus messaging system. So it's like, it's a bit weird to call it a cross-consensus messaging message, but do as you please. All right, why don't we just, build a transaction or whatever and send that? Well, there's a few good reasons for not doing this. One of them is that the transaction may not mean the same thing when it arrives at the destination place, right? Chains get upgraded. So you'd need to somehow have some versioning in there to say, well, the transaction should be interpreted with this version of your runtime, and this sort of infrastructure doesn't exist. So we wouldn't be able to use a transaction in and of itself just as is. We'd have to add something onto it anyway. A lot of the time, what you want to do isn't a specific transaction, right? You might want to, for example, make an exchange and then deposit some assets, or transfer the assets from one account and then transfer some more to another account. Yeah, and you kind of want a little bit more functionality than just what a single transaction is going to give you. And then you start saying, well, okay, let's make a transaction that can then spin up many different transactions, and then we need to programmatically alter these, and then we basically have XCM. We also have the sort of slightly milder point, but I think it's still a reasonable one. A different depending on which consensus systems are speaking to each other, there may be different ways that they, different bases on which they expect the other one to listen, right? So if we're two, I don't know, private parachains that don't really know or care about each other, they just want to, I don't know, a user just wants to move some assets across or something, then the way that you prevent one from one of the sender from like spamming or DOSing or whatever, the other one is you say, well, we're gonna have some fee structure or something, right? Now, if they're two system chains that have the same basic trust system over them, like they both have, you know, they're both set up through the governance system. You don't really need fees because you know that you're not going to spam yourself. That would be counterproductive. Yeah. So you trust the sender, the receiver trusts the sender in that instance. Same could be true if it's the parachain team and parachain team has two chains, right? For whatever reason. Then maybe they just don't have fees between those two chains. They may have fees from everyone else, but not between those two chains. And these different assumptions, you can't really do that in a transaction-based system. You just kind of have to have fees all the time because you're sort of piggybacking on all of that logic. But with XCM, we could customize this quite a lot. Okay, first point, yeah, so message format might change. You know, at this point in parachain B's lifetime, this particular message, this particular encoded transaction, I should say, might mean execute transfer, but once it gets upgraded, maybe that particular coded transaction means instead, or some other thing. And of course, what we do is we have an XCM executor, which is basically a transaction abstraction layer sitting between where the message sort of comes in and what needs to be done on the basis of it. Again, simple example, maybe you want to do 2 deposits, right? You can't really do that with a transaction. I mean, you could say, well, maybe we have a batch or something, but again, it's a bit iffy because then you're going to do 2 withdrawals. You might not have 2 withdrawals, and if you're doing something like an exchange, then you would have to have temporary accounts, and the whole thing gets a bit messy. And again, there might be instances where you want different, you want to allow logic to execute on different bases, depending on where the message is coming from, or even depending on the kind of message that it is. Might be some messages that you're perfectly happy letting execute for free, others that you don't want to. Okay, so XCM is based on the four A's. Agnostic, absolute, asynchronous, and asymmetric. Let's take a look at what these things mean. Right, so agnostic basically means we're not making any particular assumptions about the underlying consensus system. We're not expecting it to be a smart contract network. We're not expecting it to be a substrate network. We're not expecting it necessarily even to be on Polkadot, right? We're not making any assumptions at all. XCM is meant to be abstract. Absolute, by which we mean XCM is not something that's kind of like that handles failure well. We expect, if we send a message, we expect it to arrive and to arrive once. Yeah. It's sort of it makes this assumption about the delivery systems. It's not lossy. It's not like you could use UDP or something like UDP for sending XCM messages. That wouldn't work because you have XCM has no way of knowing if the message kind of arrived or not. There's no like return path that says, yeah, it arrived, or no, it didn't, send it again. Asynchronous, so when you send a message, you carry on doing what you were doing before. Like there's no waiting around for a return value or or I mean, obvious. This is kind of obvious because if we're sending it between chains, it's not like you can wait like another 5 blocks before doing the next thing, right? Now there are ways of sort of managing things like needing to have a value return, but they're a little bit a little bit work intensive. But we can look on that in a later lecture. And it's asymmetric, so you fire off a message in one direction. There's no actual assumption that the return direction even exists, right? It can be that it is one directional, that there is a channel open from A to B, but not back from B to A. XCM doesn't assume that there is a channel back open from B to A, although there is functionality that will become unlocked if that is the case. Okay. That's XCM. Now, one of the key abstractions within XCM are locations. Okay, location is it's somewhere in the world of consensus, somewhere in this like non-localized singleton space. Now, one of the ways that locations are used is to describe where to send the message. And another way that they're used is to describe where a message came from. There's 2 ways that your locations are used, but locations have a lot of different uses. It's something like a consensus systems URI. Now, you can kind of think of it in those terms, right? There is a concept of an interior location, which is a little bit like a subdirectory, or file within a directory. Yeah. So what we mean by that, we have a very particular meaning by this, though, because we're talking about consensus systems. Our meaning is that if a change in A implies a state change of B, then A can be said to be interior. Yeah. So in consensus, generally, this is a one-way street. So either a change in A state implies a change in B state, or a change in B state implies a change in A state, or neither are implied and they're independent systems. But you can't have it so that a change in A state implies a change in B state and a change in B state implies a change in A state, because that would imply that they are the same consensus system. And obviously that's not the case. Not obvious. That's only the case if A and B are the same. So this is what we mean by an interior location. Let's think of a specific example of this. Do we have an example? Yeah, kind of. Okay, so a parachain is an interior location of its relay chain. Why? Well, if the parachain changes state, then the relay chain necessarily changes state, yeah? Because the relay chain holds all of the chain heads, all the parachain heads. So if the parachains change state, then that's going to change the head on the relay chain, and that means that the relay chain must therefore have changed state. But the same isn't true in reverse. The relay chain might change state, and the parachain doesn't necessarily have to know about it. Yeah. Now, in a lot of times, the parachain will also try to track the relay chain state, but it'll be a block or 2 behind. Those changes, when they happen on the relay chain, won't immediately affect the parachain. Parachain will just look into the past and and see if it can see any changes at the relay chain. Similarly with accounts, right? An account on a parachain is like maybe a balance in an account. This is a location in consensus, right? It's a particular piece of data that we can uniquely identify within the world of consensus. Therefore, it has a location. It's an interior location of the parachain that it's on. It's not an interior location of some other parachain. Why not? Well, because if it changes, then it doesn't necessarily change the state of this parachain, but it does necessarily change the state of this parachain, right? Its state is defined as basically being entangled with as the of all of the accounts state underneath it. You know, basically it's state tree. Yeah. Similarly, if this account changes, it will alter the state of the relay chain necessarily. Therefore, it's an interior location of the relay chain as well. Okay. How do we represent locations? Well, locations are represented in a relative fashion. Okay, so a bit like a regular Unix path, file path. Yeah. So you've got like a working directory. That's the bit. You know, if you're on the console on the terminal, that's the bit that which directory you're in. I'm sure you know. And if you want to go to like the parent directory, you'll go like cd ... Yeah. ... is the parent directory. It's a relative location within the directory structure to where you are at the moment. Well, locations work in exactly the same way. And the way that we specifically encode a location or express a location in Rust is we have a number of parents up to 256, 255 as it happens, and a bunch of call them junctions, but basically like nodes in this sort of tree, in this hierarchy. And we have a bunch of different kinds of nodes, junctions. Now you can imagine junctions, if we take the sort of a file system as an analogy, different nodes there would be like a file, a directory, what do you call it? A buffer, a queue, FIFO, yeah. Symlink, yeah. So we've got there are a few different kinds of things you might find in a file system. Well, there's a few different things you might find in the world of consensus as well. So we have something like, you know, an account, a parachain, an index, a palette instance. Yeah, and this goes on. There's a few more. There is one that is, none of these are special, but there is one that you will only tend to find in a certain place. I say tend to find, nothing in XCM stops it from being found in any other place, and it's conceivable that someone might find a use for it elsewhere other than the place that we currently use it. But it's yeah, it does have a particular place that at least you will find it. And that one is the network ID. So the network ID, as you can see, basically identifies a consensus system. A system that maintains its own consensus. A few different ways of doing it. They're probably not exhaustive. There are some. They work for most of the things at the moment. So I have a text notation for this, very, very similar to file system paths. ... is parent. Yeah. Pretty obvious. Okay. Universal location was something we brought in when we were figuring out how to do bridges in Polkadot. The universal location is not a real location. It's a theoretical location. There is no specific consensus system at the universal location, nor does any consensus system host the universal location. It doesn't really exist. But it's defined purely in terms of as an axiomatic description as the location that we will define that we will that has no parents and is the parent of all top level location systems, all location systems that otherwise do not have any parents. Yeah. So, so we define it as being the location that is the parent of all locations that otherwise would not have any parent, not including itself. So the universal location doesn't have any parents, but it is the parent of all of the other locations, the real ones, that otherwise wouldn't have a parent. So for example, Polkadot network doesn't, the junction of network ID, a global consensus with Polkadot, that doesn't have a parent, right? Polkadot doesn't, it generates its own consensus. Therefore, the location that is the Polkadot network has no parent, conceptually. So, but we kind of need this. It's useful to have this theoretical location. So what we do is we say, well, all of these locations that don't have a parent, we're going to give them one. So they all become siblings. But the universal location, which is what we call this parent, this will not itself have a parent. Otherwise, there'd be some weird cyclic thing, or there'd be like a meta universal location. It'd just get crazy. So the universal location doesn't have a parent. But all of the top level consensus systems, they all have a parent that is the universal location. It gives us like a kind of route to the directory hierarchy. Yeah. If you've ever used, Windows with this SMB file sharing stuff, the way that you it's kind of like networking that isn't the internet, right? You can share files on it. The way it works is you do double backslash and then you type in and the name of a machine on the local network, and then another backslash, and then some file system that's shared on it. Now, why am I telling you this? Well, if you imagine, there is obviously no top level network position, like a network location that is the thing that contains all these machines. Like there is, because that would have to be on a machine, and it's not by definition. But still, notionally, if you go in the browser, in Windows Explorer or whatever, you can go to kind of the // location and see all these machines, right? It's still useful to have a theoretical holder for all of these things, for all of these like locations. It's useful there, it's useful here. So we have, this is what we call a universal location, the made up location that sits at the top of everything. It's very useful for bridges because it allows us to get from one place that otherwise doesn't have any parents to another place that otherwise doesn't have any parents. It allows us to express a path for moving between consensus systems, which is what bridges are meant to do, right? So that's why we bring it in. It's a useful theoretical concept. Good. So, yeah, here's an example. A universal location, bunch of top-level consensus systems, and it allows us to address one from the other. Okay, now, that's locations. Sometimes it can be helpful to express a place in the world of consensus in absolute terms. Now, this is a little bit, there are some gotchas. The reason that we didn't do this initially is because, well, initially we didn't have this concept of the universal location. And the reason that we didn't have the concept of the universal location is that there's a little bit of a problem with doing this. Problem comes about if a chain moves from becoming, say, a solo chain to a parachain, or from a parachain to a solo chain. Or potentially even between parachain identities. Yeah. And all of these things have happened, and that would mean its universal location changes. Now, if you start addressing things universally and this happens, you're totally screwed, because you have to go through every possible universal location address and change them to the new one. And that might just not be practical. It might not even be possible. There might be places that you couldn't know that universal address is being stored. Now, you still have a little bit of a problem with relative locations for any relative location that is going to be sort of be between the sort of outside world and the inside world of the thing that's being moved. But you don't have an issue as long as the two locations relative to each other are sort of either both being moved or not being moved. Both not being moved. So we don't use absolute locations very much, but it's helpful for you to know what they are, and because they are sometimes very helpful and kind of necessary for bridges. Basically, absolute locations are locations that don't have parents. So if we look at the original location definition, there we go. We've got parents, and then some bunch of junctions, right? With absolute locations, it's just the junctions. There's no parents. Why are there no parents? Well, you can't go up. You're already at the top, because the assumption is that the absolute location is taken from the universal location. And if you're already at the universal location, it's defined as there being no parents. There are no parents at the universal location by definition. Therefore, it's only possible to go down. So we only need the junctions.
So first of all, like maybe my understanding is incorrect, but is XCM only supporting like cross parachain communication, or also cross blockchain communication, as in like between Polkadot and Ethereum, etc.?
It's a language. Therefore, it can support any consensus system interactions.
Okay. And then the following question then is in the slide with the network ID, then there are a bunch of like Osama, Ethereum, Bitcoin Core, etc. Are these like preset in some system, or is it something that like is configurable?
You're confusing the language with concrete implementation. XCM is only about describing what could be, not about describing what is or what is provided.
So,
right?
So this network ID is an optional.
Like in the early days of the internet, TCP/IP supported 4 billion different possible hardware locations. It didn't mean that there were 4 billion devices connected to it.
Yeah.
Right? Merely by placing something in a language does not imply that it makes any sense or is useful or is usable at any particular point in time. No, there isn't a bridge to Bitcoin Cash, but it doesn't mean that the XCM language shouldn't be able to refer to such a bridge should it come about.
Okay. Thanks.
Okay, good. Right. So what do we use locations for? Well, I've already covered one of the most obvious ones, and that's addressing. It's useful to be able to stay where it is that we want a message to be delivered to. And it's similarly useful when a message is delivered to say where the message came from. Okay? Makes sense, yeah. We also use it for things like bridging, to be able to describe where the bridge is bridging to, like the kind of the two endpoints of a bridge. And we use it, interestingly, within the assets framework to basically name assets. You can think of locations as really being a consensus namespace more than anything specifically physical. Right now, I've given you examples of things like accounts and networks because, to be honest, they are the most generally used, right? But it's not limited in this regard. In the same way that, well, the URI system, prior called the URL system, used to be specifically used for assets you could download, like web pages and things. Indeed, I think its earliest sort of versions were like basically FTP and HTTP. They were literally things that you would hop on a protocol, say, I want this thing, and the thing would come down and be a chunk of data. Now, this has changed over the years, and URIs are basically just a namespace now. Right? It's just an abstract namespace. Now, of course, you can still use it for concrete things like web pages, but that's not what it's about anymore. It's not its proposition, its premise. XCM is kind of the same. You can use it to describe specific account, like asset holding accounts and networks, concrete things, but it's not what it's necessarily has to do. It's designed to be a general namespace. And this has some interesting consequences for when you're designing systems that are going to use XCM. Because it means you can basically, you oftentimes don't need to add extra linguistic functionality, because what you want to express can be expressed just by using locations and the pre-existing linguistic functionality. We'll see some examples of that. So yeah, cross-chain origins and destinations. So when you send a message from some place to some other place, there needs to be, you need to know, for it to be useful, you need to know where the message came from, right? It's not enough just to get a message from nowhere. It's helpful to know like who sent it. Now you're familiar, or you should be familiar with the concept of palette origins, like frame origins, yeah, accounts, root, and customized ones that you can decide for yourself. Well, there is the concept also, as it happens, of an XCM origin in frame, but XCM itself has its own concept of an origin, which is basically a location. So we talk about XCM origins, and frame kind of has this type of frame origin that hosts an XCM origin. Okay, we'll cover that a bit later in the XCM palette talk. But for now, all you really need to know is that yes, XCM has a concept of the message origin, and this is a location. A message origin can be converted into a frame origin. You can define how it is converted. And it's yeah, it can be helpful if you want to like privilege certain origins with certain abilities. Let's look at some location examples. All right, so we are sitting at Asset Hub, and we want to. This is our location. It's relative, obviously. Parent parachain 1001. So we kind of step up. The dashed line is going up. You can imagine it's got an arrowhead here. And then the thick line is going down. You can imagine it's got an arrowhead here. So we go up to the parent and then down to parachain 1001, which in this case is the collectives chain. This is how you refer to the collectives chain from the asset. Yeah, makes sense. Maybe we want to refer to a parachain account, and we're on Polkadot, we're on the relay chain. In this case, we're going to go down 2 junctions, parachain 1000, and then account ID, whatever it is. Okay. Bridges are a little bit special because they have this concept. They traverse the universal location. Okay. This thing at the top. It's not real. It's just an abstraction, indeed. So we're sitting at Asset Hub. Maybe we want to get all the way over to the Asset Hub on a different chain on Kusama, on a different network, consensus network Kusama. So we go kind of up and up till we get to this universal location, and then down and down. So that's 2 parents. And we have this node here, global consensus node, which is basically like a network node. Yeah, go on.
Instead of specifying the universe location, can we also just specify like none or null?
Well, it's not none because it is a location. It's just an abstract location.
But like the only reason it exists is because you have to specify like the parent, right? So like in theory, you could just put not null, right?
Um, hmm.
Like it doesn't actually matter, just like curious.
I mean, it's just a name, right? And it
Yeah.
feels kind of wrong to have a node. I mean, you want a node there because otherwise it's a bit weird to not have a, like, you know, you need a node to look at the, to traverse the graph. And if the node at the top is null, it seems a bit odd. Maybe root or something, but
Can I ask,
Mhm.
what's the difference between universal location and global consensus or global location? You just mentioned.
There isn't a global location, but there is. So the universal location is the location that doesn't exist. It sits above all of the locations that otherwise wouldn't have any parent. All of the locations that generate their own consensus, like Polkadot, like Ethereum, like Kusama, like Bitcoin. They all generate their own consensus without reference to each other, and yet they're still singletons. So these are like magic things. They generate their own consensus, right? And the universal location could be seen to be the collection of all the parent, i.e. the parent of all of the magic things, right? This isn't a magic thing because it relies upon this. It defines itself in terms of this, yeah? But this is a magic thing. It doesn't define itself in terms of anything else. It just exists all on its own, yeah? So the universal location, because it's helpful to group all of these magic things together, for the purpose, well, indeed, at the moment, for describing things like bridges, then we invent a location that is just the parent of all the magic things. Now, a global consensus is a node, is a type of node in this that you might find in a graph, and it's here to describe a consensus generating system. Yeah. Typically, it's used at this level, the level immediately underneath universal location. Typically. It may not always be used there because from XCM's point of view, it's just a node like account ID or parachain or something. And it might very well be that someone somewhere finds a use for this node, this junction type, under their parachain or under their smart contract. Maybe it's a smart contract and it's a smart contract that can just hold assets on behalf of all of the other consensus generating chains, right? In which case they might place that location, they might place that conceptual thing that they're managing under their smart contract, under a global consensus node. You might find it further lower in the graph. Locations are totally general and abstract. Like they're kind of meaningless on their own. Junctions are like names. They're meaningless on their own. It just depends on how they're used. Yeah. I'll give you another example, like Google.com. Now, in a URI, whatever, in this internet sort of naming scheme, we typically expect Google.com to appear before the directory path, right? If we're going to see Google.com listed in anywhere in a URI, it's usually at the beginning, yeah? Because it's a server name, right? But it doesn't mean it can't exist somewhere else in the path. We just tend to find it at the beginning. But there might be that, like, I don't know, yeah, so there's a website. Is it offline or is it me? Right, and it just checks if a server is offline or not, because sometimes maybe it's just your connection that's bad. So you can go to this and I think you just go, is it offline or is it just me.com/google.com, right? And it will go away and it will check to see if Google.com's online, and if it is, it will say yeah it is, and if not, it'll say no it's not. And this is an example where we see something that would normally be at the beginning of the URI actually farther deeper into it. Yeah. Well, we might do the same with the global consensus thing. It's normally found here, but there's no reason why it couldn't be found down here. Yeah. At the moment, I don't know of any uses of it being down here, but there's no reason why it might not be. So it's the main takeaway is global consensus is a type of junction that you might find on a node at this level down, immediately below universal location. The universal location is the location that holds all of those other locations that don't have any parents. It's kind of the orphanage or something. Yeah. All right. So if we have a bridge, if we're bridging Asset Hub to, or if we are working over a bridge conceptually, then we might want to address something on another network. So we would have to go up to the universal location in order to do that. There's no way otherwise of getting from Polkadot to Kusama, yeah, because these are independent systems. There's no way that Polkadot could have an interior location that is in Kusama, yeah, because Polkadot's state doesn't depend on Kusama's state, or vice versa. Now, in reality, of course, bridges are these kind of weird magic things that don't really sort of obey the normal rules. In reality, we have a bridge hub whose state actually does a little bit kind of depend on a state in another consensus system. So what's really happening when we send something from Asset Hub on Polkadot to Asset Hub on Kusama is it doesn't go to the universal location because there is no universal location. Yeah, it's just there. It's just created as an abstraction. What actually happens is the message goes to the bridge hub on Polkadot, and then magically, outside of really kind of the sort of regular world of consensus, it sort of teleports over to the bridge hub on Kusama using some cunning mechanism that we don't need to get into now, and then actually goes up to the Kusama relay chain and then down to the asset. So that's how that's the actual routing. But you don't need to be too concerned about that because that's not, that's kind of an implementation detail. In reality, as far as XCM is concerned, this doesn't happen. What happens is this. That's all we really care about. This is just to let you in, kind of lift the rock and see all the grisly bits underneath. All right, good. Sovereign accounts. So this is another concept you're going to come across quite a lot in XCM. It can be helpful for one location to have a particular place that is interior to another location, which it controls. Right? Okay. It's a bit of a mouthful. So it can be helpful for the treasury to have a location interior to Asset Hub, which it controls. Yeah. I.e., it can be helpful for the treasury to have an account on Asset Hub. Yeah. Where else is it going to put its assets? We call this account a sovereign account. Why? Well, because in some sense, the assets, the treasury is self-sovereign, right? It exists independently of Asset Hub, but yet it wants an account there. It's a little bit like when you've got two countries and one of the country needs an account at the other country's central bank because it wants to hold that other country's currency and there's not really any other way of doing it. Yeah. So it's like a sovereign account. In that sense, it's a similar concept. So it's a bit like if, I don't know, like France, France might want to hold Hong Kong dollars is a really bad example. It might want to hold British US dollars, right? So it might want to hold, France wants to hold US dollars. I mean, it could literally just get a ton of $100 bills, but this is not so great. It's not so scalable. So probably what it wants to do is have a US dollar account somewhere. Where would be best to have it? Well, at the main place that US dollar bills are maintained, the US dollar currency is maintained, so the Federal Reserve. So it wants an account at the Federal Reserve. Yet France itself is a current country issuer. It's not a person. Federal Reserve, like, you know, banks normally are good for people, organizations, companies. In this case, it's an entire nation. And so it probably has some special stuff going on, right? I mean, in general, it's pretty hard to open an account at the Federal Reserve. You kind of have to be something along the lines of like a country. And that type of account, where it's like a nation level thing, would be, I don't know, I'm not an economist, not a finance guy, but I would guess it would call something like a sovereign account, because it's a sovereign state that is holding the account, and therefore it kind of has its own set of rules. It's not like it could be, you know, easily, I don't know, put in prison or something, in the same way that you could do it if it's an individual or an organization that's based in the country. So in our context, it would be, suppose you have collectives that has a treasury on it, and this treasury wants to hold, I don't know, USDT or whatever, that exists on Asset Hub. Now, how can it hold USDT that exists on Asset Hub if it is in its own chain, in its own little independent world? It can't really do that unless it has some account on Asset Hub. Yeah. Well, what account would it have? Because it doesn't have like an account per se. It has a location. It doesn't really have an account. Yeah, it has a location relative to the Asset Hub, but it doesn't have an account on it. Well, it turns out that's what this is. This is the account that you get when you have a particular location relative to a system that offers accounts. You get a sovereign account. It's kind of like an external account, an account for an external entity, not an interior, not like you know, where you have like a particular key. You prove your account ID by virtue of having a public-private key pair, but rather something that's controlled from an XCM location that is external to your system. I mean, very literally, it's an account ID that is controlled by an XCM location external to the account holding chain. Call that a sovereign account. You find it very clearly on things like if you have a parachain that wants to hold dot, how does it hold dot? I mean, how would it, you know, if I don't know, Moonbeam says, right, Moonbeam holds 1 million dot on behalf of its users, what does that mean even? Like, why as Polkadot would I trust, why as an independent entity would I trust that is the case? Like, why is Moonbeam dot worth any kind of dot? Well, because Moonbeam itself holds dot. Where is the dot held? Under what? Is it the Moonbeam team that holds it? No, that would be not decentralized. That would be really, really bad. No, Moonbeam holds it. How does Moonbeam hold it? Well, Moonbeam has a sovereign account on the Polkadot relay chain, or maybe on the Asset Hub, that has that 1 million dot in it. And it's Moonbeam and only Moonbeam that can move that dot. Not the Moonbeam team, not any particular thing on Moonbeam, but Moonbeam itself must send an XCM to the relay chain or wherever to be able to move that dot or do anything with that dot. Yeah, it from the point of view of the Polkadot relay chain or the asset hub, Moonbeam is sovereign. Like it does its own thing. It's not something that that chain itself manages. Yeah. Good, but we can think of the sovereign account basically just as a mapping from a location to an account ID. There's not much. In reality, it's a very, very simple thing. It's just a convert API that's like takes a location and gives you an account ID back. Okay. So here's a very simple example. Alice on parachain A. Well, Alice, if Alice had wanted to express, or I don't know, express an account ID on parachain B, Alice would be sort of given an account ID that Alice and only Alice could control. And how would she control it? Well, she would have to control it by sending an XCM from her location here up through A, through Polkadot, and down back to B. And by sending an XCM from the location Alice to B, B would interpret and saying, I want an account ID, like I want to withdraw an asset or something, then it would look for the asset in Alice's sovereign account. Yeah. Another way that Alice could do it is not use XCM at all and just make a new key pair and use it on B. That would be another way that Alice could hold an asset on B. But if we assume that Alice isn't necessarily a human, Alice might be a logical entity, a multisig, a proxy, a palette itself, a treasury, I don't know, some random thing that exists on A, then it's very helpful for that to have a sovereign account, to be able to use XCM and get a particular account that they know is theirs and will only ever be theirs. Yeah, and we can have more complex examples. Like Alice has a sovereign account on B, but maybe there is a collective hub, collective chain has a sovereign account on A. Maybe the asset hub has a sovereign account on B. You can have lots of sovereign accounts. There's basically a kind of like matrix of chain on which the sovereign account exists and chain that is control or location that is controlling it. And there's a different account ID for all of these pairings. So, Alice on A. Yeah, collective on A and collective on B are not necessarily the same account ID. Yeah, the collective sovereign account on A and the collective sovereign account on B, not necessarily the same account ID. Asset hub sovereign account on A and asset hub sovereign account on B, again, not necessarily the same account ID. It depends on what this mapping is for A and B. There's ongoing discussion about how much of a guarantee there should be about them being the same. But nothing in XCM means that makes them be the same in and of itself. Assets. So how do we address assets? Well, assets are done pretty easily. So an asset in XCM, is given by an asset ID and some fungibility identifier, right? So an asset's a fairly abstract thing. We don't make a distinction in terms of the asset instructions between fungible and non-fungible. Just asset, an asset's an asset. An asset ID is actually just a location, so you can basically just put location here instead of asset ID. So identity is a location, just a name, right, in our namespace, in our consensus namespace. Fungibility basically is either a balance. That's this, if it's fungible, it has this like U128 balance. If it's non-fungible, then it has an instance identifier, which itself can be lots of different things. So we represent assets, we name assets by using locations. So the key takeaway here. We have things like wildcards, so we can filter particular assets. We can say, well, maybe there's a bag of assets, but the thing I'm interested in is this one. I want all of that one. Yeah, or any members of this group. That's basically what a wild asset is, all of. So we can say things like all fungible assets, all non-fungible assets. All fungible assets of this ID. Yep. Those are the kinds of things that we can say with a asset wildcard. Wild asset just means wildcard. It's just dropped 4 of the letters, make it faster to type. Good. That brings us largely to the end of this initial lecture, so I'll let you grab some refreshments now. So you should be at least now introduced to XCM, XCMP, location, sovereign accounts, assets. Next step, we're gonna look at the XCVM. This is now the, now we've got the basic concepts out of the way, we're gonna look at like the actual machine, instruction processing machine. I'll take any questions if there are any remaining. Yeah.
Hello. So my question is, we mentioned some properties of XCM, like absolute, and like for me, just natural question, like how we guarantee that the message will reach the destination, especially if it could be asymmetric channel, right?
Yeah, so we assume that the channel, the underlying protocol of the channel is not asymmetric, but but XCM assumes that the usable part of the channel is asymmetric. So for example, a bridge might keep a track of which messages have been received by the opposite side and then remove that message data from the sending side. That's generally how bridges work, right? They provide a proof on the destination side that the sending side sent a particular message, and then a proof on the sending side that a destination side has received a message in order to remove that sent message. Now this is symmetric. Well, it's not symmetric exactly, but it's bidirectional, right? There is data going in both directions. There's data delivering the message and then data removing. There is an action delivering the message, and then there is an action removing the message from the place that it was sent from, right? But it doesn't mean that the bridge delivers messages in both directions. It might still be it might only be offering the service of delivering from A to B and not from B to A. But the underlying service is provided by there being, by data going in both directions. Kind of the same with something like TCP/IP. I mean, TCP/IP is like kind of bidirectional, but one can imagine a sort of unidirectional version of TCP/IP where you can only kind of send messages that way. Or data that way, but the underlying TCP/IP stack would still allow for sort of UDP packets being sent in both directions in order to manage that flow of data going in one direction. So it's important not to confuse what XCM assumes, which is that when a message is sent, it gets there, from how the channel that message is sent on is implemented, which may indeed involve some bidirectional data flows.
Hi, thanks for the XCM introduction. Like it was very insightful. Particularly, like I have 2 questions. So how do you ensure that the XCM message that is sent and received, like the communication,
is only like a one-time usage or something? Like, is there any expiry or like?
There's no mechanism for expiring messages, nor could there be,
Okay.
because it's absolute. Therefore, when you send a message, it has to arrive. It doesn't say when it will arrive. Maybe it will arrive very, days or weeks later, but there is an implicit guarantee for any system on which, rather, let me put it another way. XCM is designed such that there must be a guarantee that if a message is sent, it does arrive eventually.
But there is no accomplishment that the message is actually like there's no callback, there's no accomplishment that the message is actually received, or it is not double sended to the same location. Like I can just reuse the message again and again. Like there's nouns or anything in the part. Is there anything as a part of the message itself that makes sure that the message is not double sended again and again, or it has to be handled by the bridge or the receiver?
No, the message assumes that it's like sending a signal. Once the message is sent, that action of sending the message implies at some point in the future that message will arrive exactly once to the destination endpoint.
So this will be the part of the message.
And that's assumed by XCM.
Okay.
It's not. I mean, maybe there are some XCM channels that just don't implement this, but they would be broken for the purpose of using XCM. And maybe people just put up with it. I don't know, but XCM is designed on the assumption that those channels exist. Why? Well, mostly because Polkadot can do that kind of thing, right? Polkadot is able to give an absolute guarantee that a message, when sent, will arrive exactly once to its destination eventually.
Okay. And one more thing which I liked interestingly about XCM is that since it's a language, then it can be used for other purposes than just sending assets. So basically, I can use it for if my parachain is for a particular use case that stores the data, I can use XCM on demand. By other parachain can use my blockchain on demand, and my blockchain can return the verified data over in the XCM encoded way. So it will be verified that it's come from the same location. Like
Yes. I mean, it is indeed just a language. And therefore it is, while it was designed for doing things like cross-chain messaging, in reality, it can be used for, there is at least one other use case that I know of that doesn't involve cross-chain messaging. Because it's an intentions language, really. Like a very, something that can express intentions on consensus systems specifically, so it's domain-specific, but a domain-specific intentions language. And one of the ways that I can imagine it being used in the future is to encode transactions, so that you can encode a transaction once and send it to any chain.
Yeah.
Right. And you just have one big global list of assets, and you know that every chain supports, say, XCM4, and therefore you're able to basically do any asset transfer across any chain that supports XCM, just with a single transaction construction system.
Lastly, so basically, if let's say I'm in a real, like just analogy to real world. So basically, I feel XCM is the system of messaging and like the educated people, how they communicate. And I use a postal service. Let's say I'm an uneducated person. I use a postal service, and these postal service offices communicate in XCM, and these offices are the XCMP. So in this case, does me as who's the person who's using this XCM need to have a sovereign account, or is it that these post offices will have the sovereign accounts on each other and they will facilitate all the communication for me?
So remind me, what's a post office again in this
post
Analogy?
offices is parachains, for example, like parachain A and parachain B. These parachains needs to have the sovereign accounts on each other so that they can communicate. But
It's not so they can communicate, it's so that they can utilize
Utilize and-
specific functionality of each other that is account ID based.
yeah, and I am the initiator of a particular action, and that it is facilitated by these, right? So in case of for example, the example you gave about the countries, France and US, they have sovereign accounts on each other. So the citizens don't need to have a sovereign account, right? The citizens can communicate just with their own nation, and the nation will facilitate using their sovereign account on the other country.
Yeah, I mean, this is one potential use case, but it's a questionable one. Sovereign accounts are not specifically there for the citizens of another chain. Maybe that's a use case, but generally it's a lot cheaper for the citizen to just interact with that destination chain directly, right? Because there's no need to use a messaging system that is generally going to be pretty expensive, right? It's going to be a lot more expensive to use one chain, to send a message across to another chain, to execute, to make a transfer, than just making a transfer, right? It's going to be like, it's kind of pointless to use XCM for that. That's not really what it's about. XCM is specifically for when you have a logical entity, like a mechanism, logical mechanism, business logic, whatever, that it sits on one chain and needs to have some effect on another chain. Then it makes sense to use XCM. And that mechanism, if it's long-lived and needs some sort of needs to use some like long-lived state on the other chain, usually long-lived state, exists underneath an account ID, and it makes sense, therefore, for that mechanism to own an account ID on the other chain. But for a citizen, a key holder to hold an account via XCM would be a bit weird. They would probably just want to interact with a chain directly.
I mean, here, could you go back 2 slides, please?
Mm-hmm. Yeah.
Oh, a few more, I think. Here.
Okay.
Here in the fungibility part of the assets, is this the actual implementation that's on like the XCM language? Or is it just like an example to show us?
Okay, this is a real, it's in Rust, but it is the XCM format.
Oh, okay. Because I was surprised to see like a U128 in Fungible.
Yeah.
We were talking about like how we usually design palettes to be generalized and to allow basically runtimes to use whatever balance type they want. Is this a limitation? Should runtimes that want to use XCM have to have a converter?
This is a elided, but actually this is a compact encoding. So in Rust, it's a U128. So if you had something that was bigger than U128 max, then it would fail to decode. But XCM itself supports arbitrary size because it just uses, well, not quite arbitrary, but it 270 bit numbers or something. So it can encode any numbers yet used on consensus systems. It's just that if you tried to use a number that was a bit too big in Rust's version of XCM, it wouldn't. But this again just comes back to this idea that there are lots of programs you can write in XCM. Most of them don't make sense. Most of them won't be supported on any given XCM implementation. XCM is like a very broad language, and the implementations of XCM will pick and choose which bits they support.
Thank you.
Hi, here. So will those messages be stored in somewhere temporarily? For example, like any mechanism, just like a message queue and dispatch a message queue one by one or batch by batch?
Yeah. So I mean, this is now getting onto the message passing system rather than the language that the messages are in. But yes, for what it's worth, there are several queues that messages go through to get from one chain to another chain, and even more queues if it's a bridged link. Specifically, there will be a an outgoing message queue on the sending chain, an incoming message queue on the receiving chain. That's only the case if it's a single hop. For example, with XCMP, it goes via the relay chain at the moment. It shouldn't really, but that's yet to be done. And therefore, there will be an additional 2 message queues, one receiving it on the relay chain, and another sending it out from the relay chain onto the next parachain. So in reality, when you're sending, at the moment, when you're using HRMP to send a message from one parachain to another, it will actually go through 4 message queues. Now, the message queues are written to be very efficient, but still, you know, it's, yeah, there is quite a lot of logic being done. Now, these message queues also, the execution message queue won't necessarily execute the message as soon as it arrives. Normally, messages are just executed through the on-chain logic, but if a message is quite heavy, if it needs a lot of weight to be executed, and this is sort of beyond what most of you will be doing, to be honest, but if a message is very heavy, it might not get executed automatically. Rather, it will sit in an overweight queue, and it has to, a transaction has to come in that basically prepays for its weight, and then actually executes it manually. But as I said, this is stuff that has to be really quite heavy before that's gonna have to happen. Yeah.
Thank you.
All right. Good. Let's call it there. Take 15 minutes, and we'll come back and start talking about the XCVM.